This will be about like towards a Platonic intelligence with a unified factored representation. One second, let me just move this. There we go. Okay. Okay, amazing. Okay, so to start off with, I want to state something obvious that you guys already know, that the world is not random, but rather it has a lot of structure, as we know. And this includes everything from like self-similarity across like many spatial scales to like physics symmetries, like symmetries in like translation, rotation, invariance of the world. As in, if you have like some laws of physics, it's going to be true here, and if you're like 1 mile away from here. And I mean, everything has structure. I mean, even the fact that objects exist and they're basically persistent across time, that's a form of structure. And the fact that there's so many common patterns across in this world, right, across many different objects, that's what leads some of us to believe in this like idea of like there's like this space of forms, this platonic space of forms, where these properties, common properties across many objects, are inherited from the space of forms. That's one way to think about what's going on, right? And obviously, this idea came from Plato, and it was pretty influential. And that's the main point of this symposium, is to talk about that. So I claim that basically intelligent agents, in order to solve their goals, they need to really understand how the world works in order to control it, right? To achieve their goals. And in order to understand this world, I argue that they must capture this structure of the world. All these different structures that the world has, they must capture it in some way. And more specifically, what I mean is that the internal representations of their minds and their brains must capture the structure of the world. So I'll talk about more concretely what this means next, but at a high level, basically, you can't really control the world without understanding how it works, and you can't understand the world without really understanding all the different structures that are in the world, right? So we face this problem in AI because in AI we're trying to create these intelligent agents, right? And we face this problem. How do we capture the regularities of the world, right? So one of the things we've been thinking about in AI is like, what if we just try to bake in some symmetries of the world through how we design the architectures of our agents, right? So this is also known as inductive biases, and I'll give you an example of like two or three of these. Is like one is like translation invariance in images. Whenever you look at an image and you see like some object, you know that the system should process the object very similarly if it's over here versus if it's like shifted over 100 pixels to the right. And this is translation equivariance or translation invariance. And we try to bake this into an architecture based on the convolutional architecture. That's what it's made to do. Another example is like whenever we process sets of objects and we don't care about the ordering of the set, like red, green, blue, or blue, green, red. We don't care about what the order is. Then we use an attention architecture in a transformer to do this kind of thing, right? And in general, this field called symmetry learning or geometric deep learning is a really big field in deep learning. And basically, the goal is how do we capture known regularities of the world into the architectures, right? And this is kind of like you're just baking in the structure of the world. But what about all the other structures in our world, right? All the other regularities. And one example I really like is like lighting invariance. So you see this lion in the dark and during the day, and you don't really know what architecture should capture this lighting invariance, right? And we don't know how to do this. So what's our solution? Well, okay, so the solution is we just try to train on a lot of data with SGD and hope that the AI will learn this underlying regularity of the world um, based on the patterns that it picks up from all of these data, from all this data, right? This is the predominant paradigm in modern deep learning currently. So the question is, does this actually work, right? And there's a lot of evidence that's showing that it is somewhat working. I mean, the AI systems nowadays, if you use ChatGPT, they can pick up on all sorts of patterns of the world and they seem to really understand the world and how it works. And even self-driving systems, they can like figure out what a stop sign looks like during the day, at night, and it seems like everything is just working. But this brings us to our position paper and our which where we hypothesize that conventional SGD in deep learning finds neural representations which are actually fractured and entangled um, in the sense that their actual internal representations are fractured and entangled. So over here, we can see that, I mean, you find a network which has a certain output behavior, but the output behavior, we visualize it as like a skull, which I'm going to get into detail how we're doing this. But at a high level, you visualize the output behavior, and the internal representations don't really match what you would expect to see if it's really like understanding the skull in a subjective way, right? And more specifically, what I mean is that it doesn't capture the underlying regularities of this world, which is the skull. So our position or our opinion is that a different kind of search algorithm, which is not conventional SGD, but a different kind of very exotic open-ended search, may be the solution to learning what we call unified and factored neural representations. And as you can see over here, the representations of the skull look much better and much more like what we would want in how you would build up the skull. So let's get into and so you might be asking, why does this matter at all, right? If the output behavior is the same. And we basically believe that the internal representation of an agent really affects its capability to generalize to new situations it's never seen before, especially OOD. Its creativity in the sense that how it like sees the world and how it comes up with new solutions or new any artifact that it can create, and especially continual learning and adaptation. And you can see over here on the top, we see that the network with the nice representation, if you perturb its weights, it has really good adaptability behavior because the skull changes in like semantically meaningful ways, versus the skull on the right, the network on the right, it has terrible adaptability and it basically just produces like a mess on the right. So let's get into the details of how we're doing this kind of experiment, right? So we're going to be using what we call like a compositional pattern producing network, or a CPPN. And basically, this is like a toy domain to study neural representations. And the goal is basically just to implicitly represent an image. And at a high level, it's inspired by the biological development process, like morphogenesis, because it's about how do you reuse existing machinery to across different like points in space in order to achieve the same thing. That's where the inspiration comes from. So let's talk about how we would represent this specific image. Let's see this pixel that's highlighted over there. What we're going to do is we're going to basically mark its XY location and its D distance from the center. And we're going to take these three numbers and just plug them into a network that is the CPPN. And after it's done processing, we're going to take its output and consider it as its HSV, or you could think about it as just like an RGB value. And that's going to be the RGB pixel value for that pixel. And if you sweep this across every pixel in the image, then you can basically visualize the entire output behavior of the CPPN as a single image. And the reason that we construct the image like this rather than just modeling like the RGB pixels is because this makes it very, very easy to visualize how the output behavior of this network is internally represented neuron by neuron. So in this case, you can literally go to each neuron and see when does it activate, at what XY locations does it activate, and you can visualize that as an image also. And one thing I want to make clear, this is probably a really important slide, is that the CPPNs are an analogy. We're not really interested in just like how you represent images, but rather these CPPNs serve as like a very useful visual analogy to think about what other AI systems like large-scale LLMs might be doing, right? And basically, the analogy is that its output behavior or the output image of the CPPN is analogous to the LLM's entire output behavior over the entire its entire output space, right? And the CPPN's internal visualization is basically analogous to the LLM's internal representation of its entire output behavior. So basically just how it models and sees the world. And because we're using CPPNs, we can just visualize how these behaviors are constructed holistically, right? Not just like in a single neuron, but seeing how it's built up over many, many neurons. And importantly, this brings us to the main point is that like two CPPNs may have the exact same output behavior, but their inner encodings could be qualitatively different, right? And this means that two LLMs may have the same output behavior, as in you can't tell them apart from what they're doing on the outside, but their internal representation and how they see the world internally may be qualitatively different. Sweet. And with that, I will actually go on a slight tangent with Picbreeder, but it'll connect back into the main story very quickly. So let's talk about Picbreeder. So Picbreeder was basically an online website for humans to breed these CPPN images to their desire. So humans would just see these images and you'd pick like two or three of them you'd like and just mutate them and keep going. It's kind of like breeding horses, right? And what you're going to be doing is just evolving the underlying CPPNs that generated these images. And importantly, one of the big things about the system is that there was no end goal. You can just do whatever you want. The humans weren't told, like, oh, you should try to evolve a skull or you should try to evolve like a cat image or something. They just said, just do whatever you want, have fun. And one caveat here is that the actual CPPNs used inside here were not like your conventional multi-layer perceptrons from AI, but rather these things called neuroevolution of augmenting topologies, NEAT. And you can imagine this as like rather than having like a dense connected network, you have like a graph of neurons that you're growing in this arbitrary way. So it's much, I guess in a way, it's much more flexible, right? And so, what would you expect to find from this pick breeder system, right? And I think most people would say that, oh, if people don't really have an objective goal in mind, then you kind of would just expect to find these super rubbish images, right? That's what you'd expect to find. But here's what people actually found these images with lots and lots of structure and basically what humans prefer, right? It's like literally things from our world. So the question is like, how did people find these kinds of things? And if you want a deep dive into how this kind of thing happened, you should really check out the book from my collaborators, Ken and Joel, on why greatness cannot be planned. And they really go into a lot of insights into like the nature of search, deception, serendipity in search, which is a really important topic, I believe, and open-endedness. And basically, they argue that this pig breeder system is like a microcosm for like natural evolution or like scientific innovation, these open-ended process which keeps discovering stuff forever. So I do want to talk more about Picbreeder and then talk about that what properties it has that why I think you should consider it as like a very, very interesting system. So first property it has is that it's open-ended. So if you think about natural evolution, it's like this divergent evolutionary process which produces all these different diversity of animals, right? And pick breeder is similarly like that. There's literally a pick breeder evolutionary tree where you just have images which are diverging and growing open-endedly. So that's one thing that's really interesting about it. Other things that are interesting about it include this idea of serendipitous exaptation. So in evolution, a lot of the traits that we ended up with, or all animals ended up with, were traits that were evolved for one function, but get repurposed later down the line for something else. So here's an example, like feathers were originally evolved to keep like the animal warm, but they later got repurposed for flight. So this is an example of like this huge task space where things are kind of just it's a more serendipitous rather than like planned ahead of time, right? And Picbreeder displays this property also. You can see that the stepping stones that they call it to like let's say look at the teapot image. Someone was actually trying to evolve a egg in a hat before someone else took that image and started evolving a teapot. So this is an example of like this machinery that was used to represent this egg got repurposed to represent this teapot. And this is like a common, very common story in all the pick breeder discoveries. Basically, every image in Picbreeder that was found is kind of displays this idea that like there it's like almost seems like random, but it's what we'd call serendipitous in how it got to the end product, right? And one final property that I want to outline is that as we know that natural evolution has developed very adaptable genotypes. And this is kind of like the emergence of evolvability, right? Because the way that our bodies and our are structured is basically it contains certain axes of variation. Let's talk about the symmetries. The way our bodies are structured really has a lot of baked in symmetries. Like for example, there's like a bilateral symmetry, and the way our organs are structured are modular. And it's just that there's a lot of structure in the way our bodies are structured, right? And the reason it's like this is because certain axes of variation during surge become much more likely while others become impossible. So, for example, if you have a mutation in your genome and your right hand gets like longer, right? Your left hand would also get longer because evolution has kind of realized that encoding this axis of this symmetry into the genome is really important because there's no point in not doing it, right? So this axis of variation where both get longer becomes likely, whereas this axis where only one gets longer becomes impossible, right? So it's a way to kind of like speed up search in that way. And Picbreeder has also shown this form of evolvability emerging. There's examples in the Picbreeder where certain images are structured in a very nice, organized way, such that their children have very fit descendants, as in they're basically producing images that humans would like. And there are some images which don't have this property, but they quickly die out because humans don't select for their children, right? So there's this like implicit pressure to be evolvable. So great. Now that I talked about Picbreeder, let's get into the actual experiments that show this internal representation that we've been talking about. So let's look into just let's pick this image of this skull, right? And see what happens. So let's take this skull image that we found at Picbreeder, and what we're gonna do is we're just gonna create a data set from it based on the mapping that we're talking about, where you have XYD to HSV, and you list out all the pixels, right? And we have this big data set, and then what we can do is just train a conventional network to recreate the skulls using all the tools from AI, right? And what we find is that the optimization works amazingly. It perfectly reproduces this skull behavior, right? But then let's talk about what happens when we start looking at the internal representation of how it represents the skull, right? That's where we see some problems. But before that, what we're going to do is quickly talk about layerization, which is not too important. So, but I will quickly go over it just for the sake of completeness. So basically, you can imagine that our neat networks that we found at Picbreeder, they're like this arbitrary graph of neurons. In order to make it compatible with the space that we're going to be doing SGD training with AI on, we're going to convert everything into a universal architecture, which is the MLP, through this process of layerization. And specifically, this will give us like an existence proof that this pig breeder solution is a solution that the SGD could have found, but it didn't. And more concretely, what we're going to be doing is just taking all the connections of this arbitrary graph of neurons and stitching them together to in the MLP to recreate the same computational graph. Okay, so this is what the internal representations look like for the pig breeder skull. This is the one found with pig breeder. So you can see that the four input neurons encode the four inputs, or X, Y, D, and we just have a bias neuron for historical compatibility. And over the layers, as you go up, you can see that the neurons encode different things and builds up the pattern at which you see at the end, which is the skull. But you can see that there's not really any redundancy. It's very, very modular in that way. It's very sparse, and it seems quite organized in how it's doing it, right? So let's look at this SGD skull now to contrast. This is what happens when you train SGD on the same network architecture to get the skull. It looks like a complete mess, right? It looks like complete spaghetti. And you can see everything ends up canceling out the end and giving you the perfect output behavior. But the internal representations are like completely just like what I'd call spaghetti, right? They're just like a complete mess. So how does this actually impact downstream, what we call like downstream tasks or something? So on the left over here, what we're going to be doing is just sweeping individual weights of this network and seeing how the output behavior changes. And you can see that it really shows you that if you sweep a weight, there's literally a weight that corresponds to the mouth opening or the left and eye winking or the distance between the eyes right there, right? Or like literally a weight controlling the jaw width. And this kind of shows you that the network kind of understands the underlying, what we would call the underlying regularities of the skull, right? These are axes aligned with how a human sees the skull. And if you imagine that the skull is an analogy to the real world and the behaviors that you would want to employ, this basically corresponds to nice changes in the actual behavioral output of the network, right? Versus if you have the network on the left, you can see that the weights kind of almost all the weights look like this. They kind of just correspond to rubbish, meaningless changes, which don't respect the underlying x-axis symmetry of the skull or any regularity of the skull for that matter, right? So this pattern is true for all the images that we've tried out. Like here's this butterfly image for Picbreeder, and here's this skull SGD image of this butterfly. You can see it's the same pattern. And if you look at the weight sweeps, it's the exact same thing. You capture the regularities on the left and you don't really do that on the right, right? Over here, you can see that one of the weights literally destroys the left wing while leaving the right wing sort of intact, which is completely not respecting that symmetry of the butterfly, right? And here's the apple image found at Picbreeder, and here's it with SED, and it's the same pattern again on the left. One of the my collaborators' favorite is like this stem angle. There's literally a weight in the Apple network that on the Picbreeder side at least that corresponds to if you sweep it, it controls the angle at which the stem is controlled at. So this really shows that the stem and the apple are like modular, it are decomposed in like a modular way in order to have this happen, right? So the question is, this is cool, but this is still like this toy domain. How does this really apply to LLMs and like real intelligent systems, right? So there is some evidence, actually a lot of evidence that these LLMs also suffer from fractured and entangled representations that don't respect the underlying regularities of the world. So let's start off with an old example from GPT-3. So in GPT-3, we ran this experiment where we had like, where you just say like, I have 3 pencils and 2 pens and 4 erasers. How many things do I have? And it gets it right. You have 9 things. But if you ask it the same exact question, but change up the item names, like I have 3 chickens, 2 ducks, and 4 geese. How many things do I have? It gets it wrong. It says you have 10 animals, right? Instead of 9. And what this means is that the machinery or the neural circuitry that it's using to count up the objects is entangled with the types of the object that it's seeing, right? So this is an example of how it could be the representation is entangled, right? So let's scale up to more modern networks. There's a lot of papers that show that like if you change like if a network can if an LLM can be really good at doing like these math problems, slightly changing the numbers in the math problems causes them to decrease their performance on that data set, which is crazy because you would expect them to be kind of robust to changes in the numbers, right? And sure, if you scale them up, this has been going away, which we're going to talk about. But let me go through some other examples too. This is
Sorry,
what,
can I ask a question?
yeah.
In the previous slide, the example about the counting, the slide before this.
Mhm.
Yeah, so uh, does it say 10 because it includes the me as well? And because it says you have 10 animals total. So if it's actually including the person who's asking the question, then it's actually not incorrect, right? I mean, just out of curiosity.
Oh, the me is not in the prompt. It's just the I have. And the fact that it's asymmetric between the two shows that's the difference, right? I don't think that's what's going on because whenever you say like how many things do I have, you don't talk about yourself, right?
Yeah, yeah, I know, but I was thinking maybe it's thinking in a much clever way that that makes us think that it's incorrect. I mean, in a sense, you could argue that it's not incorrect, but yeah, I'm just saying.
Interesting. Yeah, in that case, it should at least be symmetric on both sides, right? I also don't think it makes much sense to say 10 in this case.
Yeah, okay, yeah, that's fair.
This paper from some of my friends at MIT here, they basically showed that these LLMs, they're really, they're trained on the internet, right? And the internet has this, the world that we operate in, which is like the current world. But if you change their evaluation to counterfactual worlds, then the performance goes down a lot. And by counterfactual world, what I mean is like instead of doing arithmetic in like base 10, you do it in base 9. This is a way less common way to do things, right? Or in code execution, you change it to be base 1 indexing, then the performance goes down a lot. So in this way, you could argue that there's like it's not respecting, if you change one thing about the world, it's not respecting, it's not understanding the world where it's like it understands the regularities in a deep way where it can be robust to these counterfactual changes, right? Here's another example I really like. This is from an Anthropic Mechanism paper from quite recently, where they looked at Claude and they asked it, what's 36 plus 59? And it came out with the answer 95, which is correct. But if you look at the actual arithmetic that goes behind this answer, right? The actual neural circuitry that's happening, you can see it's using like random heuristics that a human would never even think about. It's like saying like, oh, 36 is around 30, and if you add, and it's around 40, and if you add around 40 plus around 50, it's like around 92. And it's completely like different than how a human would do this arithmetic problem, right? So its neural circuitry is kind of just like a bag of heuristics. And indeed, there's been a paper that's been written that arithmetic, that language models solve math with just a bag of heuristics, right? While still getting the answer right. So I think there's a lot of evidence that like these LLMs, their behaviors are amazing, but the way they actually represent these behaviors are very um, surprising and definitely concerning, right? And now let's talk about the counter argument, right? Just like how does scaling work? Because this is like the predominant view in AI that if we keep scaling these systems, then they should just keep getting better, right? So this is the scaling laws view, and you can see that the actual test loss or the test performance and the downstream performance on how you use these systems are getting better. But again, this is a statement about like the actual behaviors, right? And if we go on to the next slide, then we can talk about the Platonic representation hypothesis from our lab. And this is actually one of the coolest papers ever. So you guys should all definitely check this out. Basically, what they claim is that neural networks trained with different objectives on different modalities. So one could be trained on images and one could be trained in language. They show that these two models trained on different modalities and in different ways are actually converging in some sense to like as you scale up the model sizes and their performances. So over here in this graph, they're showing that as you increase the language model performance, its alignment with the vision model also increases. And the reasoning behind this is basically that as you force these networks to do more and more tasks, then the number of representations which solves all the tasks in either modality kind of has to overlap more and more. So this is all very cool, but I do want to point out that these scaling laws and this Platonic representation hypothesis are all very like statistical observations of what's happening, right? These are statistical observations of a statistical behaviors, right? And it's very unclear how this relates to respecting regularities of the world. And I think we need a lot more um, research trying to connect the two because the examples we gave in our paper where we did a survey on like all these studies that were showing that language models struggle in this task in this way or something, they're more talking about whether or not you respect some regularity of the world. And I think this is a very different way to see the world than if you just look at this as like a statistical mechanism, right? And one more thing I want to point out is that the efficiency of this scaling view, right? We don't have infinite data in the world. We only have the 10 trillion tokens of the internet. And the question is that enough? And if it's not, then this scaling view isn't really a practical way forward, right? And more practically, we need to figure out, like even now, with these large scale LLMs, why do our LLMs still have this notion of jagged intelligence, right? As in, they can do some really, really hard tasks like get IMO gold, but they can't reliably book a hotel or a plane ticket for you. So why is it that the tasks that we find so hard, like winning the IMO gold, it can do pretty nicely, but it can't do something what we seem as basic and like book a hotel. And I think the main point I want to make is that deep learning is fundamentally like a data-driven statistical learning paradigm. And I think it's a very, very fascinating paradigm that should be investigated. But I wonder if there exists like a more efficient, like regularity-driven learning paradigm, because it obviously like human intelligence and like animal intelligence, they don't just ingest like billions of examples in order to learn, right? They do something much more different and something much more akin to like understanding the regularities of the world and building on top of them. So what could this look like, right? And I think the things that would matter the most is like something like some process of complexification. If you look at like the process like morphogenesis, it doesn't just encode every part of your body at once. It grows it according to something more fundamental, right? And this is a very adaptive process which adapts to the environment and it's not just baked in. So, and importantly, I think the cool thing is that if you do this complexification in a learning algorithm, it should like try to build up the regularities on top of other regularities. In the same way that like if you go remember the skull internal representations, it's like building up like x-axis symmetry and then on top of that it builds in like the eyes from that symmetry, so it's building up symmetries on top of other symmetries in a form of like a regularity driven learning that's like bottom up. And this process of complexification should also give you build on these ideas like emergence, and I'm going to tie this back into emergence in a bit. Another thing that I think could be really important is training for adaptability. So rather than just training for to solve the task, what we really want is to train for adaptability, because I think it gives you a lot of like regularization pressure to learn like symmetries and regularities to be robust to environmental changes, right? And I think that a representation that kind of has to be robust to environmental changes is one that must capture the axis of variation, which, like, as Plato would say, like carve nature at its joints, right? And this is just personally what I think is really important. It's like serendipity. And what I mean by serendipity is that the order in which you learn things really matters. If you look at LLMs, they learn calculus at the same time as they're learning arithmetic. But humans, they always learn arithmetic before calculus because their internal representation of calculus built on top of the regularities from arithmetic. But LLMs, they kind of learn them at the same time. So they must have different circuitry if that's going to happen, right? Different circuitry for arithmetic and calculus. And that's why I think this idea of serendipity or in general curriculum learning is really, it should be important in terms of if you're doing this regularity driven learning. And I really think serendipity specifically is important because it gives you a much higher chance of finding a useful learning curriculum to actually employ, right? And if you think about it, these paradigms, what paradigm captures all of these? It's like the field of open-endedness. I think has a good, not solution, but they've been thinking about this, and I think they have the toolkit to come up with a solution that can handle all of these.
Can I ask you a question?
Yeah.
How do you think about the order related to reinforcement learning? Because you talk about this learning curriculum, and when you train a reinforcement learning agent, you often start with some very simple behaviors, and by interacting with the complex environment, they complexify themselves. So
Mhm.
I was just wondering, if if you can convert this pattern generation into some kind of a reinforced learning task, would it also have similar meaningful and robust weight or not?
That's a really interesting question. I think the on-policy nature of reinforcement learning is a really, it should be super useful, it seems. But I guess the fact that there's still like a singular objective that you're trying to solve is, I think, is a downfall. I mean, there's a lot of works in the field of reinforcement learning that show that like you train the RL agent to do one task and it masters it. But if you perturb the environment even ever so slightly, like change like for example, like change like the placement of the objects like, even a little bit, or change the color of like the how the objects are represented, everything breaks down. So I think the way they represent their task solution is still very brittle. So I think what you really need is either take the scaling route and you just have like a many different tasks, or the more better route I think would be to kind of have many different environments that it's exposed to in like a sequence and in kind of like a serendipitous way. This is kind of what happened with evolution, right? You're exposed to, this is what I'm going to talk about in the next slide too, is like you're exposed to some environment, but then you're forced to adapt according to the environment to some other environment. And then you're forced to adapt again. And this pressure to adapt is what I think really makes you robust. Because if you don't adapt quickly, then you will die. And in order to adapt, I really think you need a really strong representation. I think this is my hunch, is that I think a strong representation and adaptable representation are like one and the same.
Yeah, I also wondering how does the like models like AlphaGo looks like, because AlphaGo, when you start the reinforcement learning, they start with very poor players, and there's a similar asymmetry between player and environment, because when you improve yourself, your environment also improved. So there's a nature course of learning. Maybe there are two kind of different reinforced learning. Like AlphaGo, I think is maybe a different one, and maybe they have similar like complexification process as you mentioned.
Yeah, it builds in a lot of these things together, but I mean, AlphaGo obviously solved Go, so that was a huge impressive result. But I'm still not sure that it's training to be adaptable. It's kind of like its objective is to train to solve the objective, right? The cool thing about evolution is that it's like you could say that it's optimizing to be a good fit for the environment, but it's implicitly optimizing for adaptability because everything is always changing, right? So if someone shows that like this, if there is a pressure to like adapt, then that would be pretty cool, I think. Yeah.
Thank you.
Yeah, so I guess zooming out a bit, how does this relate to like the Platonic viewpoint and what you guys have been thinking about for a while, right? So I think the space of forms that people have been thinking about, obviously, like you could argue that it's like this is where the real world and all its patterns come from, and I think intelligent agents are fit or like trying to be intelligent to that world. So obviously, indirectly, the space of forms is going to leak through. But I guess the cool thing is that I've been thinking about that. I guess maybe you guys can add something to the conversation. Is that does this space of forms directly does the internal representations of a good agent in turn like does this mind come directly from the space of forms, right? So I guess you could argue that like just as like you have this like aspirational ideal of like this Platonic shape, and you have the real instantiation of it in this pyramid, the same way that real intelligent agents are kind of trying to mimic this aspirational ideal of this like perfect mind that can understand the regularities of the real world. But this is all just speculation, right? So cool. Yeah, this is something I'd love to get your guys' thoughts on. And just to wrap up, I'd like to thank my collaborators, Jeff, Joel, and Ken, for making this work possible. And with that, thank you.
Thank you. That was very interesting. Uh, questions? Doug.
Yeah.
Yeah.
Yeah, hi. So as I understand this, the training process. So first of all, this is beautiful. And you can sort of see where having things modular like this now allows you to do cognition rather than just like randomly emitting motions and stuff. But it seemed to me that you're still training on something. And so then the question is the difference between this way and the old way of doing things that instead of training to fulfill a task, you're training towards some criterion. In other words, somebody is somewhere is saying, oh, gee, that actually looks like something, I'll keep that one, as opposed to keeping the spaghetti. Um, is that a fair way to look at it? So, or your evolutionary adaptability, that's another criterion. You survive, maybe you did it this way, maybe you did it that way. So the tasks are different, but the criterion is the same.
Yeah, so I do want to say they did some experiments after Picbreeder happened where they asked people to explicitly evolve the skull, where they're like, your goal is to get to the skull and get there as quickly as possible, and that did not work at all. So even if it did, I think that you would end up with like kind of like a brittle skull. I think the key important thing is the fact that this environment that people are selecting images, right? So this environment of selection that's happening, like the selection pressure, is extremely complex. It's as complex as the human brain because they're the ones doing the selecting, right? And more importantly, it's changing. After the skull gets discovered, no one thinks that that's interesting anymore, and you need to figure out a different adaptation that's more interesting than the skull, right? So I think this pressure to adapt again is the thing that's creating these good representations.
But
That's
there
the
is, oh, go ahead.
Yeah, that's the reason that the skull, like, there's a weight that corresponds to the mouth opening, because that's the axis of variation that humans find the most interesting, right? So in the same way in the real world, there's some axis of variation that are gonna be like on Earth that are gonna be useful, and these are the ones that intelligent agents need to capture, right?
But there's some point at which whoever's doing it said, okay, I'm done. That's my picture.
So that's the thing. When one person gets it done and they upload their picture, the next people start evolving. It's like this open-ended process. It never stops, right?
Okay.
Mhm. Okay, I
Chris.
think. Okay, yeah, Chris.
Yeah, thanks. This was very nice. I just wanted to comment on the question in your last slide about the effects of the world of forms on the agent. Yeah, the one right after that.
This one.
No, the one right after that. No,
This one.
I'm sorry, that one. Yes, that one. I mean,
Yeah.
the wonderful thing about organisms is that we are part of the real world.
Mm-hmm.
So, to the extent that this idea of forms informing our structure or the structure of the real world, then that applies to us too, and in particular to the way that our minds work. So, in thinking about this picture, um, we have lots of intelligent agents that are already part of the world.
Mm-hmm.
And so their interactions with the rest of the world are just part of the way the world works, right? So
Yeah.
if the way the world works is driven by some, abstract principles, symmetry and so forth,
Mm-hmm.
then um, our behavior with respect to the world is driven by those same symmetries. Whereas with intelligent agents, we're trying to use an abstraction from certain features of the real world to design an intelligent agent when we're coming
Yeah.
up with any machine learning scheme.
Yeah.
And this suggests, at least to me, that it's an interesting approach to think about, to design the simplest possible agent you can and just turn it loose, which I think is what you're describing to some extent with Picbreeder. Is that a fair assessment of the proposal you're making?
So you're so the way I see it is that, like, let's talk about like a concrete example of like planets, right? Let's say that like the space of forms informs physics, right? And the way that particles interact. And these particles, you run them for a long time according to like gravitational laws, and they form this imperfect planet, right? With some bumps and things. But this planet is like emergent from the laws of physics, right? But this planet, you could argue it's kind of like trying to inherit the property of being a perfect sphere, right? So not only were the laws of physics inherited from the space of forms, but also this emergent planet is trying to be another idea from the space of forms, right? In the same way, I think that intelligence, in the sense that you said they're just agents in the real world, they're just complex systems. They're just made off of small little tiny particles following the laws of physics. But as a global whole, the emergent phenomenon of the brain could be something like mimicking, trying to mimic something more Platonic in that sense, right? That's the way I've been seeing it, if that makes sense.
Yeah. Okay. Thanks.
Mhm.
Thank you. Brian.
Hey, Akarsh. Yeah, I had a question about the framing around the way the CPPN and I guess open-endedness is kind of this top-down signal where you're having someone or something, like some maybe like God or something, choosing the things that actually are desirable than less desirable, and having this top-down view even for the SGD model too to like match this target. But is there a more bottom-up view of the open-endedness where like there
Yeah.
isn't a kind of loss function that's given from top down, but like it's just kind of an emergent property of the system. Maybe it's like stability or persistence or something.
Yeah,
I guess.
I would actually classify the Picbreeder stuff as bottom up. I would classify the SGD ones as top down because the SGD one kind of what I feels like it's doing is that you have this like block of marble and you're chipping away at different places in order to get the shape that you want, right? But I see this Picbreeder one as in you're starting out with like a small no network which has like no neurons and you're building up the first neuron which encodes x-axis symmetry and then you build up something else which builds on top of that symmetry and you're building this bottom up, this layers and layers.
Selection process is done by humans, right? And
The
that,
selection process is done by humans, yeah.
right. So that's the top down signal I'm kind of describing is
Oh,
like,
oh.
yeah.
Oh, you're saying if you can replace humans with some other signal.
Right. Like something that is more in the nature of the system or the physics that it would exist in a world rather than having a human top down being like, okay, this is something I like, this is something I like, this is something I don't like.
Yeah, so I don't think any like if you do something like any like if you try to put an equation onto it, I don't think it's gonna work because it's not gonna be nuanced or diverse enough. We are doing some experiments and trying to make like an automatic pig breeder with VLMs, using VLMs, and even that is like we're like struggling a lot. So I think the environment that you're exposed to really does have to be extremely rich and complex in
I
order
guess
to
maybe in that perspective, maybe the human itself is the environment that the picture kind of lives in, and it has to survive or persist in, and that's kind of how you would
That's
imagine.
right. I think that's the right way to view it. So then the question is, if you want good networks and good AI systems, right? You need to subject them to the right environmental pressures. And I think the way that you subject them matters a lot. So I'm a big fan of like, this pressure it to adapt. I think that's the right way to think about it.
Cool. Thanks.
Yanbo.
Hey, so I also have two questions about fairness. So the first one is different architecture might suitable for different thing, and that's what you explained. But I think there are some example in video games, like some people want to challenge themselves, so they constrain themselves, like I only have one weapon to win the game. And when they decide to do this, the entire playing process become very complex. You can't play game like usual people, and usually people can play game in a quite a decomposable way. They have a clear semantic meaning of doing this, doing that. But when you apply this constraint, you have a lot of things that locally looks nonsense. So just wondering first, the data is generated by CPPN, but you train it on MLP. So this kind of I don't know if it's very fair to compare this. And this leads to another question is CPPN has a very carefully designed architecture and training process and some details, but MLP, I know that there are some tricks or regulations on MLP. I was just wondering, have you tried to optimize MLP in order to make it symmetric? Because if you don't do that, then this comparison it's also might feels unfair to compare. Yeah.
Yeah, so in terms of the first of all, in terms of the fairness, I mean, in this paper, it's like a position paper, and we're not proposing Picbreeder as an algorithm that's supposed to compete against and that everyone should use, right? It's more like to inspire like that fact that this algorithm has some cool properties that were associated, even though we cheated and we used humans in the loop, we used a different neat network. It's supposed to inspire ideas that maybe we can extract some insights and turn this into an algorithm which can compete against SGD and do better. So we're not trying to be fair. We're trying to cheat and come up with an algorithm which, in some way or shape or form, found something interesting, right? Yeah, I think that's the grand goal of this kind of research. And your second question was about what was the second question?
It's about how many efforts you apply, you put on optimizing MLP in order to make it
Oh yeah, yeah.
reasonable.
Yeah, so obviously you can't bake in any explicit symmetry into the network. We did try a large set of experiments using like weight decay, and we even tried to make the target symmetric, like the target image perfectly symmetric to see if it was perfectly symmetric, would it pick up? And the answer is it almost never picks it up. There are like one or two seeds out of like 20 seeds in which you have, if you have the right weight decay with the right um, symmetry aspect with the right architecture, because we tried out different architectures also, then it ends up working. But it almost never actually works. Yeah.
Yeah. Okay. Yeah. There was a recent study that adding noise to the weight of the model instead of adding weight decay. I'm wondering, have you tried that? Would it make the map become more symmetric?
No, I haven't tried that. I really doubt that these things like this would qualitatively change the learning dynamics to make it capture regularities versus not capture regularities. I don't think any simple trick like that would do it. One of the cool ideas that I'm investigating with the undergrad here is like basically trying to see if the network, if we try to make the weights predictable, because predictability is like a very specific type of signal that could qualitatively change what you learn, right? Because weight decay is more like a simplicity bias where you want to regularize it towards like low weight norm. But I think that if you try to make it predictable, that's not the same thing. It's not the same as simplicity. It's completely different. So I think there are ideas in which it could change, but honestly, I don't even think that would work that well. I think what you really need to do is like rethink what's going on and what the pressures you are that you're optimizing towards. And I think the pressure to adapt is probably the biggest thing that needs changing. I think that would fix a lot of things.
Interesting. Yeah. Thank you.
Hmm.
Axel.
Yeah, great paper. I really loved it. I'm an experimental biologist, so for me this was really up my alley. I really loved
Thank
um, the idea, and I think objective functions are something very fundamental, and I think this really sort of shows it. And I think one of the things you could interpret from your paper is there might be a trade-off between complexity of the objective function and how controllable the outcome is. As you noted yourself with when you tell people to select for a certain outcome, Picbreeder doesn't work anymore. How
you.
fundamental do you think that trade-off is?
The trade-off between having a fixed objective function and what else?
Yeah, sort of the richness of your objective function
Oh,
and how well you can determine the outcome of your optimization process.
yeah. So I think the fact that Picbreeder is not able to optimize directly and then it has to take this like serendipitous path through the search space. I think there needs to be more research like quantifying just how important that is. That was like kind of like the point of the paper that we don't really know or understand what causes good representations. And it would be cool if like we could figure it out, right? So I think that it feels that like the serendipitous search is very, very important. I can't exactly rigorously tell you why, but the reason it feels that it's like important is because it combines this pressure to adapt while making optimization easier because you're not just optimizing for a single skull, right? Because that's like really, really hard to do. You're optimizing for either a skull or a cat or a dog or anything else that a human would want, right? So I think that is like this serendipitous search kind of makes optimization easier, and the pressure to adapt is something that's obviously good and that's hard to satisfy. It's hard to optimize towards. So then you need this serendipitous search to optimize it, if that makes sense.
Doug, you're muted. Sorry.
Okay, great. So we find that natural languages pervasively omit system component relations, which has to affect whatever happens when you use written stuff to train these machines. But then in that context, that made me think about your Apple example. So does the network know that the stem is a component of the whole apple, as opposed to just something that's sitting next to it? So that's this issue of not only, so engineers think in terms of systems and components. So not only do you have two things sitting next to each other, but is the stem a component of the apple? Is the color red a component of the apple? And that's different than, computer scientists is always talking about overlapping sets. And so the system component thing is structural, completely different thing. So how smart is this guy?
Yeah, that's a good question. So over here, I mean, you can see that there's feature maps that correspond to just the apple, and there's a feature map that corresponds to just the stem. And at some point in the network, they get combined in order to make the apple with the stem. So,
Hmm.
I mean, that's kind of like the modular decomposition you would expect in an ideal world if you wanted these two things to be decomposed, right? So I
Hmm.
think the feature maps they basically show that it's like basically perfect in terms of what you would, if you want that. But then the question is that the right decomposition, right? That's one of the things I've been thinking about is like, how do you know it's like basically, if you imagine the skull, you can decompose it any number of ways, right? You can decompose it along this way, which I like, or another way, which you might like. And they're both what we would call unified and factored. So then that really begs the question is like, in a ground truth manner, what makes a good representation? And personally, I feel like that definition should be grounded in the set of future tasks that you may want to adapt to, right? I have this thought experiment I like a lot, which is like if you evolve like a cat on Earth, right? But you have the same identical cat evolved on Mars, and they're identical in their behavior. One may have different axes of variation in its genotype based on the past and future environments it's going to be exposed to, right? Because the future environments in Mars are going to be different than the ones on Earth. So they might be very different in that.
Since you're thinking about that, I was debating whether to mention this, but since you're at MIT, I don't know whether they still teach what the frog's eye tells the frog's brain, an ancient MIT paper that I think is one of the more important papers in biology. But basically, frogs' eyes only see things like edges, light, dark contrast, and a couple other things. The rest never gets through to the brain. So if the fly is not moving, the frog doesn't even see it. So they have a basis set of universals like Kant would talk about. Um, you and I have a different set, more complex. On the other hand, the frog could say, oh, that's a needless over-complexification of the world.
Yeah.
And so there's some thought that goes into what is your basis set.
Yeah, exactly. And it should be grounded in what you need to do now and what you may need to do in the future, right?
Well, good point. I guess evolution decided that for the frog. So, okay.
Yeah, that's very cool. What's that paper called? What the frog's
Oh,
eye tells the frog's
yeah.
brain?
Frog's eye, what the frog's eye tells the frog's brain. Um, let me get you the author so you can find it. Everybody, I think, has passed away.
Oh,
Jerry Lettvin, Lettvin, and Humberto Maturana, who also passed away. Anyway, it was an MIT thing. The biologist, he told me, laughed at him when they presented. But basically, this stuff is hardwired into your nervous system. Oh, and he finally got it published in the IEEE proceedings.
very cool. I will check out that paper. Thanks.
Yeah.
Santosh.
Yeah, so so do you think that the pressure to adapt is very different from the pressure to generalize, which is a standard component of any MLP optimization, right?
Yeah, I think honestly, I don't think we know the answer, and I think that it feels like it should be very, very different in that sense because I feel like the pressure to adapt, if you construct it in the right way, I think it should be like a much stronger pressure that regularizes your neural network a lot more. I don't have evidence for this concretely yet, but that's just a feeling that I have. Yeah.
Okay.
Yanbo.
Hey, I want to ask another question. I just realized this study might deeply related to computational complexity theories, because when you gradually simplify or grow the CPPN, it's really like you have a Turing machine and you have a sequence of program. You add bits to complexify the program, and in computational complexity theory, there's a very interesting bias called Solomonov induction or algorithm probability, which the exponentially prefer shorter programs. And they proven this kind of distribution, this kind of bias has some very beautiful and powerful universal property. And one of the reasons they have this 2 to the minus graph complexity is because they have some they are actually somehow growing the program. So wondering, have you considered such a connection between them?
Yeah, so what I have been thinking about a lot in terms of like, is simplicity like a one, is it a good pressure toward that you should strive towards, and two, is it enough, right? And for one, I do think that it's very interesting. Obviously, you want simpler things rather than more complex things, but the question is that whether it's enough is I'm not so sure about that. Is because simplicity is basically supposed to be a how do you call it, like a heuristic for what you really want, which is like generalization, adaptability, etc., right? And I think that if we can optimize for generalization, adaptability directly, we don't really need simplicity. And in oftentimes I'm beginning to think this more and more, is that they may not even be that correlated. They're probably correlated up to a point until they strave off. So for example, in this skull example, we have a toy experiment. Obviously, it's not that conclusive because it's just a toy CPPN experiment. But whenever we regularize it with weight decay, we find solutions which are way, way lower weight norm than this nice, elegant modular solution, way lower weight norm. So in the traditional sense of L2 regularization, you would say it's a simpler representation, right? But it turns out to be way less adaptable still compared to this nice modular one. So maybe some sort of simplicity mechanism or compression is not exactly what you're looking for. And it's supposed to be just a heuristic for adaptability, which is what you really want.
Yeah, so what I exactly want to say is I just intuitively feel that evolution, especially growing and evolution putting together, might directly give you such bias of algorithm probability, and maybe that's why CPPN and this kind of open-ended process give you such clean result.
Oh, you're saying it's simple in like a different way, according to like
Yeah,
Coleman.
yeah.
Like,
Like when you start with some seed and you add something, you are exponentially more likely to have shorter evolution tree. That shorter evolution tree, like if you in terms of something like assembly theory, they are more simple.
yeah.
And uh, I feel that this architecture gives you such bias.
Yes, yes, definitely. I 100% agree with that. Yeah. It gives you a specific kind of like graph bias towards smaller graphs of
Yeah.
neurons.